students, myself GV and Dr. Kiran Yadav. In this session, I will give a brief introduction about what is quantum mechanics. So first let us see that what are the basic principles on which quantum mechanics is based, or like how the quantum mechanics view the problems around. So in quantum mechanics, all the matter particles has wave-like properties. This is also called as particle-wave duality. Therefore, a particle, according to quantum mechanics, can behave as a wave as well as a particle. Particle waves are described in a probabilistic manner. In quantum mechanics, we cannot exactly specify the position of a particle or a wave. We can only define the probability of finding the particle waves in a region. So electron does not whiz around the nucleus. It has a probability distribution describing where it might be found. Okay, and this reason allows for seemingly impossible quantum tunneling effect, and about which you will study later in the upcoming sessions. Some properties come in dual packages, can't know both simultaneously to arbitrary precision. The third most important formulation on which quantum mechanics is based is Heisenberg uncertainty principle, according to which there are certain properties which can't be determined simultaneously. These are like position and momentum, okay, energy and time. So we cannot determine the position and momentum of a particle simultaneously. If we know the position, then there will be some error or inaccuracy in determining the momentum of the particle, and if we know the exact value of the momentum, then there will not be an accuracy in the position of the particle. Similarly, energy and time can't be determined for a particle simultaneously. And the last point is the act of measurement fundamentally alters the system. This is called entanglement. So this will be discussed in later sections also, so you can easily understand this in upcoming session. So basically there are three basic formulations on which quantum mechanics is based. First is wave particle duality. Second is particle waves are described in a probabilistic manner. We can't specify the exact position or location of a particle wave. Third property is the Heisenberg uncertainty principle. So this is the quantum mechanical point of view. So why this study of quantum mechanics arose, or what led to the study of quantum mechanics? So this problem arose: why was red light incapable of knocking electrons out of certain materials, no matter how bright? So as we know, in photoelectric effect, when light is incident on the surface of material, then electrons are emitted from the material. However, when red light was incident on a material or a photoelectric material, then there was no ejection of electron from that material. Yet, blue light could readily do so even at modest intensities. This was called the photoelectric effect. It was not possible to exactly explain the photoelectric effect using the quantum mechanics. So this effect was explained considering the formulations of quantum mechanics only. Classical mechanics could not explain this effect. Einstein explained this effect in terms of photons and won Nobel Prize. okay, where the energy of each photon is given by h nu. Without quantum mechanics, we could never have designed and built semiconductor devices, computers, cell phones, etc., lasers, CD, DVD players, barcode scanners, surgical applications, MRI, nuclear reactors, atomic bombs. Physicists did not embrace quantum mechanics because it was generally novel or weird. So, if someone explains you classical mechanics, it can be easily understood by the common sense. Like you will say, yes, such things happen. But if someone will say someone will talk about the quantum mechanics, then the concepts that are there in quantum mechanics are not that easy to be captured by a normal mind. Like you will have to think differently. So this is the famous double slit experiment where the wave nature of light is considered. Here the double slit experiment is shown, and the nature of light is considered as particle and wave both, and the results for both the cases are shown. If the particle is if the light is considered as a particle, then the particle will cross through one of the slits and there will be a dot, or there will be a center dot produced as a result in case the light is considered as a particle. On the other hand, if the light is considered as of wave nature, then the waves will cross both the slits and there will be a certain pattern obtained as a result, where there will be bright and dark fringes. The pattern that is obtained on the screen is an interference pattern characteristic of waves. So light is a wave, not particle. So when this experiment was performed on real life, then this pattern was obtained, which suggested that light is a wave. But repeat the experiment one photon at a time. Over time, the photons only land on interference peaks, not in the troughs. So let's discuss about classical mechanics. Then we will see how the transition from classical mechanics to quantum mechanics took place. Classical mechanics is the mechanics of everyday objects like tables and chairs. The origin of classical mechanics was laid by Newton. He gave 3 basic laws. First law is an object in motion tends to stay in motion. Force equal mass time acceleration was the second law. And the third law was for every action there is an equal and opposite reaction. These 3 basic laws led to the foundation of classical mechanics. These Newton's laws were given in a book which Newton published, whose name was Newton's Philosophiae Mathematica, which was published in 1687. Then the major finding in the field of classical mechanics came in 1788, where Lagrange's mechanics came into picture. Then in 1834, Hamilton gave some other methods to describe the equations of motion. Then in 1864, Maxwell gave the 4 equations, and then 1900 Boltzmann entropy equation was discovered. So these were the major breakthroughs in the field of classical mechanics. However, there were several experiments at the beginning of the 20th century which needed an explanation. Okay, so like the ultraviolet catastrophe, the Stern-Gerlach experiment, and the hydrogen spectra. these were some of the experiments whose explanation according to classical mechanics were not sufficient, and Newton tried to explain for these phenomena, and his explanation were quite insufficient. So the classical physics is basically described by Newton's laws of motion, and it is successful for explaining the motions of objects and planets. So the equation written here is a famous equation of classical mechanics. In the end of 19th century, experimental evidences accumulated showing that classical mechanics failed when applied to very small particles. So to explain the behavior of very small particles, the quantum mechanics came into picture. So we will see in next session that how quantum mechanics explain the behavior of small particles, and what were the like experiments which classical mechanics could not explain and the quantum mechanics explained easily. So we will continue the discussion in next session. Thank you.